Do you think the moon is inhabited?
Well, listen, it seems logical to me. There's light, isn't there? Until the 17th century, apart from the Sun, the Earth, and the Moon, we only knew of 5 other planets in total. 2 centuries later, the most widely accepted model to explain the formation of the planets in our system predicted the existence of a very small number of other worlds in our galaxy. In 1950, the vast majority of theoretical models still suggested that the formation of planetary systems was a relatively rare phenomenon. Then, equipped with increasingly powerful telescopes, by looking up at the sky and observing the stars, we discovered planets orbiting stars other than our own, exoplanets. Today, we know of 4,168 of them, including 677 multiple planetary systems, that is, systems hosting more than one planet. The group of planets accompanying our Sun may not be unique after all, and it may even be that we have found competitors for it, among which is perhaps, to this day, the most extraordinary extrasolar system we have ever discovered. The system of the star-transiting planets and planetesimals. Small telescope, one located 39 light-years away from us, this very small star. A red dwarf whose radius is barely larger than that of Jupiter is called ultra-cool, with its surface temperature barely reaching 2,200 degrees. Up until now, nothing too extraordinary, except that this little sun hosts a group of 7 exoplanets, all rocky and similar in size to Earth. With such a small star as their companion, one might think that all 7 planets in the system would be frozen on the surface. But that's not taking into account the fact that they are all 5 to 30 times closer to their star than Mercury is to our Sun. So close that all these planets must have ended up reaching a state of synchronous rotation. That means they always show the same face to their star, just like the Moon does with the Earth. The first 2 members of the group, Trappist 1b and Trappist 1c, are most likely so because of their proximity to the star. Celestial bodies scorched by stellar fire, hostile worlds that a runaway greenhouse effect may have turned into hell. A burning hell on the side constantly exposed to light and freezing on the dark side where eternal night reigns. From this vantage point, almost certainly without any observer. It must be possible to clearly see the other planets of the system, reflecting the pale red light of their star. So close to each other that they must all be clearly visible. Placed on the surface of the inner planets of the system, you would see the entire sky vault moving at considerable speeds above your heads. Because Trappists, a B and a C, orbit so close to their sun, that a year there lasts only 36 hours and barely 58 respectively. But let's leave behind these scorched worlds and head toward the 3 inner planets of the system, which are by far the most interesting. Because they are all located in the so-called habitable zone. That is, in a region where the energy received from the star is enough to allow water to remain in a liquid state. The first Trappist, a D, is a world where a year lasts only 4 Earth days and is of an intermediate size between Earth and Mars. On the hemisphere constantly exposed to the sun, everything may still be arid and hot. If there was ever water here, it's possible that it completely evaporated and eventually fell back as snow on the other side of the planet, where the sun never rises. Eventually, over time, this could have formed immense ice caps there, frozen by the eternal night. But between these 2 extremes, at the boundary between fire and ice, day and night, there may be more favorable conditions. On a narrow strip between the 2 extremes, one might be tempted to imagine a bit of melted snow feeding a few streams, winding through an alien landscape tinted with the red of the small star. From transiting planets and planetesimals, small telescope. 1D, you wouldn't have to wait long before you could admire a full moon, or rather, a full Earth. Because the 2 other inner planets of the system are frequently visible there beyond the horizon. The first transiting planets and planetesimals, small telescope, 1E, is surely the most promising and welcoming. If your goal is to find water in its liquid state, climate simulations seem to show that if this world has a significant amount of water, then, because of its distance from the star, it would necessarily be found here in liquid form on its surface. And this regardless of the composition of its atmosphere. And water in the Trappist 1 system, we think there could be a lot of it. Up to 5% of the total mass of the system could be made up of this precious molecule. By comparison, our planet only contains 0.02% water. In other words, it's believed that it's not impossible to find 250 times more water on this world than on Earth, which might make Trappist 1e an ocean planet. These types of worlds, whose existence is still theoretical, wouldn't just be covered with water as far as the eye can see, they would be almost entirely made of water. We're talking about planets where no rock breaks the surface, where there are no beaches to wash up on, and where the oceans could be hundreds or even thousands of kilometers deep. And depending on their composition, their age, the temperature conditions there, and their distance from the star. These worlds, made mostly of water, can end up covered on the surface by a thick layer of ice over a liquid ocean. They can even be what are called sauna planets, meaning entirely covered by a thick atmosphere of burning water vapor. And beneath this, like under the lid of a pressure cooker, there are oceans on the verge of boiling, kept in a liquid state by the pressure from the thick layer of clouds. It is believed that up to 75% of the total mass of an exoplanet of this type could be water. That water around a core made up of heavy elements, which, during the formation of the celestial body, would have sunk to the center. In the case of a planet with 6 Earth masses and made up of 1/3 water, simulations show oceans whose depths can reach nearly 13,000 kilometers. By descending into these immense layers of liquid water, after about 100 kilometers down, you would eventually encounter an exotic form of matter, an arrangement made possible by the hellish temperatures and pressures that prevail at the bottom of what is called hot ice, an ultra-compact water crystal. And this type of crystal should form no matter what the temperature is on the surface of the world. So let's not deny ourselves the pleasure and keep speculating. Going back to transiting planets and planetesimals, small telescope 1e. If this world has a deep ocean and is gravitationally locked, as its proximity to its star suggests, then some simulations predict the appearance of strange weather phenomena. On its perpetually sunlit side, a supercharged atmosphere may have developed, to the point of eventually producing a cyclone of considerable power and practically immortal, due to the absence of land masses to stop it. A continuously fueled cyclone that would just keep spinning there. Half of the globe, continuously bathed in light, would thus be constantly swept by gigantic storms, storms fueled by air currents always moving in the same direction. From the hot side to the cold side at the top, and from the cold side to the hot side at the bottom. On the other side, plunged into continuous darkness, there would be oceans covered with thick ice. At the border of fire, sun, and ice, the dense air and thick clouds would leave the surface in endless twilight, perpetually bathed in a dark red light, like on Trappist Vendée. But now, let's leave this planet and head toward transiting planets and planetesimals, small telescope 1F, the second inner planet of the system. From its surface, our previous home is clearly visible and appears about the same size as our moon, seen from Earth. Slightly colder than the previous one. We can assume that on this planet there is an endless ice sheet, covering the entire celestial body with its ice. As for the last 2 planets located on the outer edge of the system, these worlds could very well be terribly cold and inhospitable. It is unlikely that there are conditions favorable for the emergence of life there, because their distance from their star is unfavorable. The first one, with an average surface temperature estimated to be around -80 degrees, could very well be a generalized Antarctica, hiding beneath these hypothetical bands of clouds, a solid and frozen surface. As for the last planet in the system, with an average temperature estimated at -100 degrees, it may be an ocean planet covered with ice on its surface. Well, you might be thinking that I say maybe too often. The reason is simple. For now, it's impossible to know exactly what these planets are like. Because even though we know their radius, mass, and distance from the star, the composition of their atmosphere remains a great mystery. And the atmosphere is more than just important. To illustrate this, let's take the example of Gliese 581c, a very promising super-Earth here, compared in size to Earth and Neptune. Of this exoplanet, which orbits on the outer edges of its star's habitable zone, we know the mass is about 5 times that of Earth. And its surface temperature has been estimated to be between -3 and over 40 degrees. These values were obtained from the theoretical albedo of this world, which is its ability to reflect light. Except that the temperatures of a body also depend a lot on the composition of its atmosphere. For example, on Earth, without the greenhouse effect, the average temperature wouldn't be +15 degrees, but -18. And when we have fun simulating different atmospheric models for Gliese 581c simulating different atmospheric models, then the surface temperature ends up being within a certain range, in a range going from -40 to 100 degrees. Hot, liquid or cold, frozen, temperate or sauna. Most of the time we don't know, so we work with what's most plausible. And many candidates for ocean planets could just as easily be little corners of paradise or hellish pressure cookers. In the case of transiting planets and planetesimals, small telescope, only one thing is certain. All these planets are too large and too light to be made of rock alone. Even so, this system is still one of the best targets discovered so far for searching for life outside our solar system. However, there is still a downside: its star. Because a red dwarf, by spinning very quickly on its axis, can create a magnetic field hundreds of times more intense than that of our Sun, to the point that it may have heated, by transferring energy through induction, the cores of the 3 planets closest to it. If that's the case, transiting planets and planetesimals. Small telescope, 1B, could end up with a partially molten surface, the scene of continuous volcanic activity. And then, a small star can also mean a big problem. Because red dwarfs are much more active than stars like ours during the first few billion years of their lives. Their surfaces are regularly shaken by violent eruptions, which can even double their brightness in just a few minutes, and generate stellar storms, powerful enough to erode the atmosphere of the surrounding worlds over the long term. Thus, the 7 planets of Trappist 1 may well have all lost their water and atmosphere a long time ago. Because of these repeated outbursts from their star, they may now be nothing more than worlds with charged surfaces. Unless they formed farther from their star than they are today, or unless they have a magnetic field strong enough to serve as a shield. In short, the question of the habitability of these planets remains largely open. And if the secret to being boring is to tell everything, then the Trappist-1 system is one of the most fascinating. One thing is certain: if it turns out that systems like this have favorable conditions that might allow life to develop there, then that would be very good news for the search for extraterrestrial life. Because 85% of the stars in our galaxy are red dwarfs, which are more or less similar to Trappist. Which means that if life could develop around these stars, it would instantly become a potentially very common phenomenon in the universe. And as the icing on the cake, life here could very well take all the time it needs to become more complex. Because red dwarfs have a lifespan that is measured in trillions of years. A small eternity compared to the lifespan of our Sun. Afterwards, before we can go and check all this out for ourselves, we might have to wait a little while. Because it's 39 light years away from us. With a spacecraft traveling at the speed of the Voyager probe, it would take about 685,000 years to get there. Thousands, millions of other possible worlds. Hot, temperate or cold, frozen, liquid or sauna, inactive, calm or volcanic, small, restless and rocky, swollen, cracked and filthy. Up there certainly exist worlds just as exotic and unfamiliar to us. As exotic as the sight of the Sahara would be for a Marin. Worlds of steam, water and humidity, or vast deserts of fire and aridity. The questions remain unanswered. Habitable may be inhabited. Who knows? If on one of them, we will one day be able to identify an atmosphere that, like ours, has been transformed by living activity, an atmosphere whose chemical composition has eventually been changed by biological activity. Maybe even see who. It's a form of advanced civilization.
Up there, what do you think is out there?
There are other inhabited worlds.
I said this is the only one that's inhabited.
No, there's the moon too. The proof is that there's light.
About the moon, you're not wrong. We're sure there's at least someone there since you're always there.